going to look at how we prove that certain problems are not expressible in fixed point with counting, leading up to examples mentioned on this slide, such as satisfiability, Hamiltonicity, and three-colorability. We will start with the graph property of Cai-Fürer-Immerman, and we'll get there by first considering the tools needed for proving inexpressibility. So first, we consider an extension of first-order logic with counting quantifiers. Now, counting quantifiers are quantifiers of the form as depicted here. There exists I element x such that phi, which is to be read as just that this is true in a structure if there are at least I instances that one can put for the variable x, which will make phi true. Now, this is equivalent to a formula of first-order logic, if phi is a first-order formula, which simply asserts the existence of I different elements. Take the conjunction over j strictly less than k between 1 and I, saying xj is not xk, right? Say that they're all different, and the conjunction over all j of phi xj. So you substitute the free occurrences of x and phi by xj, conjunction over all j between 1 and I. So this just says there are I distinct elements satisfying phi. So adding these counting quantifiers changes nothing to the expressive power of first-order logic. You can replace them. But what we do is we also require that we can only use k variables. So now, while ck is contained in first-order logic in terms of expressive power, it is a proper extension of lk. Because what you can do with k variables in first-order logic is not sufficient to do what you can do with k variables in first-order logic with counting, because here you use a single variable, where to expand it out into first-order logic, we needed I distinct new variables. So every formula of ck is equivalent to a formula of first-order logic, but one with more variables. Now it turns out that just like for fixed-point logic, we could show that any sentence of fixed-point logic is equivalent to some infinite collection of sentences of Lk. Similarly, every sentence of fixed-point logic is equivalent to some infinite collection of sentences of ck for some constant k, which means that if you have two structures which cannot be distinguished by any sentence of ck, they cannot be distinguished by this formula phi. Right? For every phi, there's a k. So it's that two sentence structures which cannot be distinguished by ck cannot be distinguished by the formula phi. This equivalence relation, ck, which says that g and h here, I'm considering it for graphs, cannot be distinguished by a sentence of first-order logic with counting quantifiers using only k variables. There's a reason why I've switched to talking of graphs rather than structures. This equivalence relation turns out has a sort of history in the context of graph theory, particularly of graph isomorphism. It has another characterization, and this is known as the k-dimensional Weisfeiler-Leman equivalence, or to be precise, the equivalence relation corresponding to counting logic with k+1 variables is the same as the k-dimensional Weisfeiler-Leman equivalence. I'm just roughly stating what the combinatorial definition in graph theory is. We're not going to use this formulation much in this course, but I wanted to stress that this is a kind of very well studied family of equivalence relations, family indexed by k, which arises very naturally in many different contexts. So in the context of graphs, typically we say that two graphs are equivalent. You partition the k-tuples of vertices in a graph into classes, where the partition is the coarsest partition satisfying the condition that when you have two tuples in the same class, then counting the number of substitutions you can make into them to get into another class, any other class Pj, is the same for u and v. In other words, in the tuple u, you look at the number of vertices v you can substitute in the ith position. Okay, well, let's not call it I. Let's call it the nth position, because I is the index of this class. You look at the number of substitutions you can make in the nth position so that the resulting tuple is in the class Pj. So for each L and J, you look at this number, and if u and v are in the same class Pi, then for all L and J, this number must be the same for both u and v. So you take the coarsest partition satisfying this, and that is the k-dimensional Weisfeiler-Leman partition of tuples of vertices on a single graph. And this turns out to be the same as saying that these two tuples are not distinguished by any formula of ck plus 1. And then you get an equivalence relation on graphs by saying that the two partitions you get on the two graphs are the same in a certain sense. So the k-dimensional Weisfeiler-Leman equivalence relation is in a precise sense an over-approximation of the isomorphism relation, in the sense that if you have two n-vertex graphs, then if they're isomorphic, then they are equivalent with respect to k-dimensional Weisfeiler-Leman equivalence for any k. If you let k be as big as n, the number of vertices, then this is the same as isomorphism. But in general, as you increase the value of k, you get an ever finer equivalence relation. So it approaches isomorphism in the limit. And for n-vertex graphs, that limit is reached certainly by stage n. So for any fixed k, you have an equivalence relation which approximates isomorphism. And it's a tractable approximation in the sense that it's decidable in polynomial time for any constant k, where the degree of the polynomial depends upon k. Now, this is a very useful family of, so the point is you can approximate isomorphism by fixing some small value of k, and you get an equivalence relation which is coarser than isomorphism, but easy to decide, and you can get it closer and closer to isomorphism by increasing the value of k. This, as I said, arises independently in many different contexts. It has equivalent characterizations in the a combinatorial form, which is what I had on the previous slide in terms of coarsest stable partitions. In logic, this due to Immerman and Lander, in terms of equivalence in counting logic. In algebra, the original definition by Weisfeiler and Leman, in fact, was in terms of what are called coherent algebras, but that was for the equivalence relation that we would call, we now call the two-dimensional Weisfeiler-Leman, or equivalence in C3. The generalization to k-dimensionals is really, this sort of combinatorial interpretation due to Babai. And Holmes showed how to generalize the coherent algebra formulation, original one of Weisfeiler, to arbitrary dimensions as well. Turns out that the same, these equivalence relations have characterizations in terms of linear optimizations, that is, lift and project hierarchies over linear programming relaxations of isomorphism. We may return to this topic in lecture 4 and look at this a little bit. All of this is to tell you that there's a fairly robust notion of equivalence here, of this family of equivalences, which has been studied from many different aspects. And one thing I haven't mentioned in here is this sort of game theory characterization, which is what we're going to look at in some detail next. So, Immerman and Lander, when they defined originally a pebble game for the counting logic CK. It goes as follows. We have, again, our two friends, a spoiler and duplicator, using k pairs of pebbles playing on a pair of structures. A and B. Now, as before in the pebble game, spoiler chooses an index I, that is one pair of pebbles, and chooses a set of vertices in one of the structures, right? Duplicator has to respond by choosing a set of vertices in the other structure. For instance, spoiler might choose a set of vertices in B. Duplicator has to respond with a set of vertices in A, right? By vertices, I just mean elements of the structure. With the proviso that the set that the duplicator chooses has the same size as the one spoiler shows. Now spoiler places the pebble AI on an element of Y, and duplicator has to respond with a pebble BI on an element of X. Note, spoiler could have chosen a subset of A here. Duplicator would have had to choose a subset of B, in which case spoiler would be placing an element on an element of the set duplicator chose. So it would be BI over here and AI over here, because spoiler is allowed to play on either structure. And again, at the end of this, we have these pebbles, at most k on each structure, covering certain points. It defines a partial map from A to B, right, where you take the point pebbled by AI to the point pebbled by BI. If that map is a partial isomorphism, the game can continue. If it's not, spoiler has won and demonstrated a difference. So let me roughly relate this to the logic. Remember, we had a pebble game for LK. Let's consider a formula. If you have a formula phi of LK, which is true in a structure A and false in the structure B, then spoiler has a winning strategy in the K-pebble game, and the winning strategy is really given by the formula. Whenever if the formula starts with an existential quantifier, then spoiler places a pebble corresponding to this variable on an element of A, which is a witness to this. Anything that duplicator chooses in B will not witness this because the formula is false, and therefore you have a pebbled position with a pebble A1 and B1, which are distinguished by the formula psi. If you have a universal, let's call that x1 for all x2 theta, then what spoiler does is choose a counterexample to this universal. Since it's assuming the universal is false in B, you'll choose a B2, which is a counterexample to this. Assuming the formula is true in A, anything that duplicator chooses the formula theta will still distinguish it, right? It'll be true of A1 and A2 in A, and false of B1 and B2 in B, and so on. And since there's at most k variables in the formula, k pebbles suffice for spoiler to force it into a position where at the end we have a quantifier-free formula that distinguishes the pebbled positions, and therefore they're not a partial isomorphism. Now, what happens with the counting quantifier? If you can say there exists m elements x such that phi, okay, and suppose this is true in A and false in B. What is spoiler's move corresponding to such a quantifier? Well, to say there are m elements x such than phi, spoiler will choose the set of elements in A which witness this. Now, if this formula is false in B, then any set of m elements that duplicator chooses in response will contain at least one element for which phi is false. So spoiler places a pebble on that element. Duplicator has to respond with a pebble on an element of this set. And now, again, inductively, we have a pebbled position where phi is true in A and false in B. And so the spoiler can carry on. So that's the sense in which this game of Immerman and Lander captures exactly counting quantifiers, and it's an easy proof that if duplicator has a winning strategy for P moves, then you can't distinguish the two structures with any sentence of CK of quantifier rank at most P. There is another characterization which is rather useful, which Hella gave in terms of bijection games. Here the connection with the logic is less obvious. It requires a little bit of an argument, but the games are rather convenient to use in proving inexpressibility results. So the game is again played on a pair of structures NP with pebbles A1 through AK on A and B1 through BK on B. Again, at each stage, spoiler chooses a pair of pebbles which are going to move. Let's call them AI and BI. And duplicator has to respond to this with a bijection between the universe of A and the universe of B. And this bijection has to respect the fact that for pebbles which are already on the board, right, so everything other than the ith one, or this bijection should take the element covered by AJ to the element covered by pebble BJ. For convenience, I would just write H of AJ is equal to BJ. Then spoiler chooses now where the new pebbles are going to go. So in effect, duplicator in this bijection is giving a response to every possible placement of any of these pebbles AI and BI, and those responses should form a bijection. And then spoiler chooses the element of A on which AI is going to go, and BI goes on its image under the bijection. If the partial map between the pebble positions is not a partial isomorphism as before, then spoiler wins. And duplicator has a strategy to play forever if and only if their two structures are not distinguished in CK. In fact, I stated the other one for fixed quantifier rank, you could do the same over here. Duplicator has a strategy to play for P moves if and only if they're not distinguished by any sentence of CK of quantifier rank at most P. Okay, so I've given you two different pebble games for the counting logic. Let me argue why these two games are equivalent. So if duplicator has a winning strategy in the bijection game, you easily get a winning strategy in the Immerman counting game. That's easy to see because suppose duplicator has a winning strategy in the bijection game, and suppose spoiler chooses a set X. Then duplicator takes the bijection that it would have played in the move and looks at the image of X under this bijection, and that gives a set of the same size on the other side, which is duplicator's response in the counting game. Similarly, if spoiler chooses set in B, then you take its inverse image under the bijection H, and that gives duplicator's response in the counting game. And it's easy to see that the conditions are satisfied. In the other direction, what you do is you define, suppose you now have, duplicator has a winning strategy in the Immerman counting game. Now, in the structure A, you take this boldface A here is the set of positions currently pebbled, right? And you consider the equivalence relation on elements of A defined by two elements A and A prime are equivalent if substituting them into the ith position. What is the ith position? I is the pebble that spoiler is moving. So you're basically looking at anywhere the pebble could move to, and you say two positions are equivalent if the resulting positions, right? Two elements are equivalent if the resulting positions cannot be distinguished by a formula of CK. This forms a partition of the universe of A. You look at each of the parts of this partition, and by hypothesis, if spoiler were to choose that set, duplicator has a response on the other side in the counting game, okay, of the same size. And the point is those responses must form a partition of B, right? Because if they have an overlap, then you would have two things which are CK equivalent in A, which are not CK equivalent in B, and that would violate the assumption that duplicator has a winning strategy in the counting game. Okay, so the partition of A induces a partition of B. Stitch these together to get your bijection H. Okay, so that's a sketch of the proof. I will leave it as an exercise to fill in the details. And this tells us that Hella's bijection game characterizes the counting logic just like Immerman-Landra's bijection game does. And now we're ready to apply this to show that the polynomial time graph property that is not definable in FPC, the Cai-Fürer-Immerman construction. I should say the famous Cai-Fürer-Immerman construction. This is a construction which has been used in many, many contexts to settle many, essentially to prove lower bounds for many classes of algorithms. The key idea is it constructs a sequence of pairs of graphs, gk and hk, one for each value of k, which cannot be distinguished in the k-variable counting logic, but such that there is a polynomial time decidable class of graphs that includes all gk and excludes all hk. It follows from this that this polynomial time decidable class of graphs, which includes gk and excludes hk, cannot be defined in FPC, right? And that was the main point of the proof. But the consequences of the construction are much richer, much beyond the immediate application to showing that a polynomial time property is not in FPC. Because another consequence is that there is no fixed value of k such that the k-dimensional Weisfeiler-Leman equivalence is the same as isomorphism, which was another open question settled by the Cai-Fürer-Immerman and Immerman construction. Okay, so let me say something about how we obtain the graphs gk and hk. Start with an arbitrary graph G. And using this, we can define a graph xg by replacing every edge of G with a pair of edges and every vertex with a gadget. This is the gadget. Okay, I've displayed this gadget for a particular vertex of degree 3. Okay, so imagine you have a vertex of degree 3. So what we're doing is we're replacing each of those 3 edges by a pair of edges, namely this pair, and this pair. And we're replacing that vertex V by this gadget consisting of 10 vertices and connected in the way I've shown. Okay, so to understand this connection, think of it this way. The vertex V has 3 neighbors, let's call them W1, W2, and W3, right? So we have 2 vertices facing W1. We call them AVW1 and BVW1, sorry. So VW1 is the edge going upwards. And we have 2 vertices A and B associated with that. We have 2 vertices A and B associated with the edge VW2 and 2 vertices V and W3 associated with the edge W3. Note that at the other end of this will be a vertex AW1V and BW1V, which will be part of the gadget corresponding to W1. Okay. So those are the 6 vertices. In the 6 outer vertices of this gadget. In the center of the gadget, we have another 4 vertices. And these 4 vertices, well, they're 4 because this has degree 3. In general, the number of vertices in this core will be 2 raised to the power d minus 1, where d is the degree of the vertex. Basically, there is 1 vertex in here for every even size subset of the neighbors of V. So what are the even size subsets? There's the empty set, there's the set 1, 2, the set 1, 3, and the set 2, 3. And these 4 vertices are connected to these 6 outer vertices and to nothing else, each one to 3 of them. Namely, vertex V empty set is connected to all the B vertices, And in general, a vertex V labeled by the set S is connected to A BWI if I is in the set S, and to B VWI if I is not in the set S. Right? So the empty set corresponds to all the three B's. V12 will be connected to the A for index 1 and index 2, and B for index 3, and so on. Okay. That describes the graph xg. We get a different graph x tilde g, which is, we do exactly the same thing, but we choose one particular vertex v, and instead of the even size subsets of its neighbors, we take all the odd size subsets of its neighbors and do exactly the same construction. That's the only difference. And the claim is that if you start with a graph which is connected and has tree width at least k, then the two resulting graphs are not isomorphic. This only requires the connectedness of G, actually. The two resulting graphs are indistinguishable in CK. That's where the assumption about tree width comes. And I will say a little bit more about what tree width is in just a moment. And then, as they argue, we can construct a polynomial time property separating the xg and x tilde g. And the second thing, the CK equivalence, is proved by a game argument, which we'll argue by the Hella game. The original proof in Cai-Fürer-Immerman didn't say anything about tree width. They relied on the existence of balanced separators, but tree width gives a nice way of arguing it based on certain cops and robbers games. Okay. The construction is a bit complicated if you haven't seen it before. So let's explore some properties of this construction. And maybe I'll do that before I talk about tree width. So the key point of these gadgets, I'll call this A1, B1, just for simplicity, A2, B2, A3, B3, and I will label these empty set 1, 2, 1, 3, 2, 3. So the empty set is connected to B1, B2, and B3. This will be connected to A1, A2, and B3. This will be connected to A1, B2, and A3. And this will be connected to B1, A2, and A3. And the key property of this is that I can take any two of these three pairs of ABs and swap them, and that gives me an automorphism of the gadget. So for any pair, there's an automorphism of the gadget swapping the two elements of that pair, right? Because if I switch A1 and B1 and switch A2 and B2, that's basically, I can permute the four central vertices and leave those two fixed and get an automorphism. That's kind of obvious because if I have the even size subsets of 1, 2, 3, then swapping two elements, the sort of membership of two elements, still gives me all the even size subsets. If I swap just one, then I don't get the even size subsets. So there is no automorphism of the whole gadget which switches just one pair, but for any two pairs, there's an automorphism of the gadget that switches them. That's the key property of these gadgets. And that's the one we're going to use. So this is why when I, for one particular vertex, I get, I replace the gadget with an odd gadget, I can kind of move this oddness around to anywhere else in the graph because the graph is connected. It doesn't matter which vertex, is the odd one out. I can, by permutations of the gadgets, which are automorphisms, hide this oddness anywhere in the graph. And that's the key to the game argument we're going to use. Okay. But before I get into that, I want to tell you a little bit about what tree width is.